Bismillahirrahmanirrahim. So let's solve the second problem of this week. Example two. This problem is also related to a simply supported beam, but this beam is subjected to a combination of loading. The examples that we have solved this till this point, um, in every example, beam was subjected to one load, either a point load or a UDL or a VDL. But now we will solve some problems, that will have a combination of loadings. So this beam is subjected to a point load at midspan having a magnitude of 15 kilonewton, and it has a UDL. The intensity of UDL is 5 kilonewton per meter, and it has a point moment acting at support A. So this is another new concept that we will learn in this problem, that how to deal with such roller or hinge supports that are subjected to point moment. The magnitude is 80 kilonewton meter. This point is A, this point is B, and this point is C. The objective of this problem is again to draw a shear force diagram, bending moment diagram, and elastic curve of the speed. So this beam will have two reactions, as it is a simply supported beam and there is no horizontal load acting. We can call this reaction as RA and this reaction as RC. These distances are 5 meter and 5 meter. Okay, so first step to solve the problem is to determine the reactions of this simply supported beam. For that we will apply conditions of equilibrium. Let's apply sigma Fy equal to 0, and our convention will be we'll take upward forces as positive. So if we start from this side, Ra is the force acting in the upward direction. We are applying sigma Fy equal to 0, so this moment will not be included in this equation. Next, if we move in the rightward direction, we have this 15 kilonewton force acting in the downward direction, minus 15 acting in the downward direction, and there's this UDL. We know that the magnitude of UDL can be determined by calculating the area of this rectangle made by this UDL. So 5 into 5, and it's acting in the downward direction. So make it 5 into 5, and then we have RC acting in upward direction. So plus RC, and this sum is equal to 0. Now if we rearrange this equation, what do we get? We get RA plus RC equal to 40. And in this equation, we have two unknowns, RA and RC. So we cannot solve this equation. We need another relationship between these unknowns. So for that, we will apply the other condition of equilibrium. Let's take sigma MC equal to 0. And for this equation, our convention will be we take clockwise movement as positive. Now let's start from this side. So RA will produce moment in clockwise direction about point C. So our equation will be RA into N is the lever, and then this moment is acting around point A. This moment is in clockwise direction, so again it will be positive, plus 80 kilonewton meter. And as this is a moment by itself, so we do not need to multiply it with any lever arm. Now let's move in this direction, and then we find this 15 kilonewton force, and this force will produce moment about point C in counterclockwise direction. it will produce moment about point C in counterclockwise direction. So it's negative 25. And how much is the lever arm? Lever arm about point C is half of this 5. So 5 divided by 2, and this will be equal to 0. If we solve this equation, we get the value of RA from this equation, and that value will be 5.75 kilo. RA is equal to 5.75 kilo. And if we plug in this value of RA in equation number 1, we will get the value of RC, and RC from this equation will come out to be 34.25 kilonewton. So this way we have calculated the reactions of this beam RA and RC. Now the next step is to see that how to divide this beam into number of portions. So for that we'll start from left side, and we see that at point A we have a support, a reaction is there, and a point moment is there. As we move in rightward direction, we reach point B. At point B we have a point load acting. So it means that this point B should be a dividing point between first and second portion. So our portions will be, first portion should be AB, because we have a variation in loading at point B, and then from point B we have a UDL. A UDL is starting at point B, and as we move in the rightward direction we have this UDL, and it ends at point C. So our next portion should be BC, and this brings us to the end of the beam. It means that we will have two sections, two portions in this beam, portion AB and portion BC. Now we will consider these portions one by one, and for both portions we will write down the equations for shear force and bending moment. So let's start solving these portions one by one. Portion AB first. How much is the limit of x for portion AB? Portion AB, x will vary from 0 to 5 meters. Our first step is to draw a free body diagram for portion AB. For portion AB, we will consider a section somewhere over here. So let's draw the free body diagram for portion AB. We have a hinge support here. This is the location of the section. We have a reaction here, whose magnitude is known, and it is 5.75 kilonewton. This distance is x, and we have a point moment here, whose magnitude is 80 kilonewton meter. Is there any other force present in this region for this portion? I think we have section, the forces that are exposed by the section. Shear force acting in the downward direction V, and the exposed moment M. And this is our convention to draw the shear force in the downward direction and moment in counterclockwise direction. Now we will write down the equations for shear force and bending moment. For shear force, we will apply sigma Fy equal to 0, and our convention will be we take upward forces as positive. So how many vertical forces are there in y direction? Starting from this end A, we have this force 5.75 kilonewton acting in upward direction. So it is positive 5.75 kilonewton. This moment will not appear in this equation because it's a moment, it's not a force. And then we have this shear force V acting in downward direction. So minus V, this is equal to 0. And if we rearrange this equation, we get V equal to 5.75 kilonewton. So this is the equation of shear force for portion AB, and there is no variable x in this equation, so write down the equation for bending moment. Sigma mx equal to 0, and our convention will be we take clockwise movement as positive. So if we write down the equation of movement for this portion, we start from this side, point A. We are taking some of movement about the section or about this point here. 5.75 kilonewton force will produce clockwise movement about this point. We take 5.75 and the lever arm is x. Movement is in clockwise direction, so it is taken as positive. And then we have this 80 kilonewton meter movement. This movement is also acting in clockwise direction, so it should be taken as positive 80 kilonewton meter. And as again this is a movement, so it does not need to be multiplied with any lever arm. And then we move in this direction. Here force V is already passing through the section. It will not produce any movement about the section. And then we have movement M in counterclockwise direction. So minus M equal to 0. So this is the equation of bending moment for this portion. Now if I rearrange this equation, I will get M is equal to 5.756 plus 80. And in this equation we have variable x, which means that the value of bending moment is not constant throughout the portion AB. So we will have to calculate the value of M for point A and point B. At A, x is equal to 0, so M is equal to 5.75 into 0 plus 80. And this means that M at point A is equal to 80 kilonewton meter. Now this time we have a different situation as compared to the problems that we solved earlier. That we have a hinge support at point A, still we have some value of bending moment, and this value is equal to 80 kilonewton meter in this case. Why this is so? Because we have a point moment acting at point A. So I told this to you guys earlier as well, that at hinge support and roller support and free end of a cantilever beam, the value of bending moment is equal to 0 unless there is an externally applied moment. So this thing we have seen in this problem, that we have external hinge support, but the value of bending moment is not equal to 0 at the external hinge support, rather it is equal to the externally applied moment, which is 80 kilonewton in this problem. So that's something new that we have learned in this example. So this is the value of bending moment at support A, and let's calculate the value of bending moment at point B as well. At point B, x is equal to 5 meter. So M will be equal to 5.75 into 5 plus 8, and this gives us the value of M equal to 108.75 kilonewton meter. This is the value of M for point B. You can use the subscript A and B as well if you like for these M values. So this completes our calculation for portion A. Now let's move to portion BC. In portion BC, we will have to draw the free body diagram first. We will consider section somewhere over here, and this section, somebody asked me for one of the problems that we solved earlier related to UDL, that why we took the location of section before the resultant of UDL, why not after the UDL, the resultant. So the answer is that we can consider section anywhere. Before the resultant or after the resultant does not matter, because this resultant is just sort of an imaginary force acting here. By imaginary, I mean when we will make calculations for shear force and bending moment, we'll be considering So you can consider section here or section outside after the resultant. It does not matter. When we will be calculating the bending moment for portion BC, we will consider whatever part of UDL is present on the left side of the section. Okay, let's see how. The value of x for portion BC will vary from 5 to 10 meters. And let's draw the free body diagram for portion BC. Here is support A. This is our section. 15 kilonewton point load is in here, and we will. This is support A. Okay, this is support A, and we have a reaction here. The magnitude of reaction is already known. How much is that? It is 5.75 kilonewton. 75 kilonewton, and we have part of UDL present here. How much is the intensity of UDL? This is 5 kilonewton per meter, and we have a point moment actually here, which is 80 kilonewton meter. What else? Is there any other force present in portion BC? The exposed shear force B and exposed bending moment M, and this point is point B. The location of the section with respect to support A is X. So I think this completes the free body diagram for portion BC. Now let's write down the equation for shear force and bending moment. For shear force, we will write down sigma Fy equal to 0, and our convention will be the upward forces as positive. So let's start from this end. 5.75 kilonewton acting in upward direction. 5.75 kilonewton force acting in upward direction, and then we have this 15 kilonewton force acting in downward direction. So minus 15 acting in downward direction, and then what about this part of the UDL? Now, for considering this part of the UDL, we have to consider this much distance. Now, how much is this distance? The distance between point A and B is 5 meters. The distance between point A and the location of section is x. So how much is this distance? Is x minus 5. Okay, so portion of UDL present on the left side of the section, the length of that portion is x minus 5, and the intensity of UDL is 5 kilonewton per meter. It's acting in the downward direction, so we take it as negative. 5 is the intensity, and the distance is x minus 5. And this will be, and then we have this downward shear minus v, and this will be equal to 0. So this completes the equation for shear force for portion BC. Now, if we simplify this equation, we will get V is equal to 15.75 minus 5x. This is the equation of shear force for portion BC. Now, in this equation, we have variable x. It means that we need to calculate the values of shear force for point B and point C separately. So, if we calculate it for point B, x is equal to 5 meters. So, V at B is equal to 15.75 minus 5 into 5. Right? So the value of shear for point B from this side is minus 9.25, minus 9.25 kilonewton. And for point C, x is equal to 10 meters. So VC will be equal to 15.75 minus 5 into 10. So if we calculate the value of shear for portion for point C, we will get minus 34.25 kilonewton. So this way we have calculated the value of shear for portion BC, and we have got it for both the points, point B and point C. Okay, now let's go ahead and calculate the value of bending moment for these points. For that, we'll take sigma mx equal to 0, and our convention will be we'll take clockwise as positive. Alright, so let's write down the equation. Now, starting from this end, 5.75 kilonewton force acting in upward direction will produce clockwise movement about the section. Okay, so we take 5.75 into x, alright, into x, and as it is producing movement in clockwise direction, so it will be taken as positive. And then this 80 kilonewton meter, it is also acting in clockwise direction, so we take it as positive 80 kilonewton meter. Then what else? 15 kilonewton force is producing counterclockwise movement about the point, about the section, so it will be taken as negative 15. And how much is the lever arm for this 15? Distance between this force, perpendicular distance between this force and section is x minus 5. So into x minus 5. And then this UDL, how much is the intensity of UDL? It is 5 kilonewton meter, and it will produce movement in counterclockwise direction, so it should be taken as negative minus 5 into. Now, how much is the distance of this UDL or portion of the UDL present on the left side of the section? It is x minus 5. We have done this while calculating the shear here, minus x minus 5. So this 5 into x minus 5 is the magnitude of the resultant. And what will be the location of resultant? It will be acting somewhere over here. Okay, and how much is this distance? The distance between this resultant and the section. This distance is half of x minus 5, because it is acting at the center of x minus 5. So how much will be the lever arm? It will be x minus 5 divided by 2. And then this minus m, which is acting in counterclockwise direction, and this should be equal to 0. So in this way, we have written the equation of moment for portion BC. Now, if you simplify, now there are two options. You can either simplify this expression and get a simplified expression and then calculate the moment for point B and point C, or even if you like, you may not simplify it and then just plug in the values of x for point B and C and get the values of moment. So it is up to you, whatever you like. But I can tell you what will you get if you simplify this equation. If you simplify this, you will get m equal to minus 2.5 x square plus 15.75 x plus 92.5. This is the equation that you will get if you simplify this expression. Now we can calculate the value of moment for point A and point B and point C. So at A, at B, not A. We are in portion BC. So at B, x is equal to 5 meters. So m at B will be equal to minus 2.5 into 5 square plus 15.75 into 5 plus 92.5. And if we solve this, we will get m is equal to 108.75 kilonewton meter. And this value of m is exactly equal to the value of m that we got from portion AB. And we have discussed that whenever there is no point movement at any given point, then the values of movement that we get from either side of that point, that should be same. Okay, at point C, how much is the value of x? X is equal to 10 meter. So MC minus 2.5, 10 square plus 15.75 into 10 plus 92.5. And if you solve this equation, you will get m equal to 0. Now, is it logical or not? This is logical because at point C, we have a roller support. And at roller support, we have discussed that if there is no point movement or external movement acting at external hinge support or roller support, the value of bending moment should be equal to 0. So at point C, the value of bending moment is 0. And this is totally logical because this is a roller support. Whereas at support A, the value of bending moment is equal to the externally applied bending moment. It's equal to 80 kilonewton meter. So this completes our calculation of shear force and bending moment for portion AB and portion BC. Now next step is to draw shear force diagram and bending moment diagram. So to draw shear force diagram and bending moment diagram, I will be considering the beam again. So here we are. We have a simply supported beam. A point load is acting at the center. Magnitude of point load is 15 kilonewton, and there is UDL. The intensity of UDL is 5 kilonewton meter per meter. We have a point moment here with a magnitude of 80 kilonewton meter. We have already calculated the reactions. Reaction at support A is equal to how much? It is 5.75 kilonewton, and reaction at support C, this point is point B. So reaction at support C is equal to 34.25 kilonewton. Span length 5 meter and 5 meter. Okay, so this is the beam. Now, in order to draw a shear force diagram and bending moment diagram, we need to draw some guidelines. We need a guideline at every location where we expect some variation in shear force and bending moment. So we expect variation at the support at all the points actually A, B, and C. Let's see. So this is our 0 0 line, 0 0 line, and we are plotting shear force diagram SFD, and our units are kilonewton to draw this SFD. Now, if we look at the values of shear forces that we have already calculated. So for portion AB, the value of shear force is constant. Where is that? The value of shear force is 5.75 kilonewton for portion AB. Okay, and this is positive. So let me draw a positive line, and the ordinate is 5.75 kilonewton. I don't need to write down the units because we have written the units outside this diagram. So this is 5.75, and then what about the next portion, portion BC? In portion BC, the value of shear force is a variable. At point B, it is minus 9.25 kilonewton, and at point C, it is minus 34.25 kilonewton. So here we will have minus 9.25 kilonewton, and at point C it is minus 34.25 kilonewton. Now the question is that how should we join this point with this point somewhere over here, which is 34.25 kilonewton. For this, we will have to look at the degree of the equation of shear force. So here is the equation of shear force for portion BC. The equation of shear force is 15.75 minus 5x. What is the degree of this equation? Degree of this equation is 1. What do we mean by degree of equation? By degree of equation, we mean the highest power of x involved in that equation. So in this case, we have only one, like x is appearing in only one term, and the power of that x is 1. So the degree of this equation is 1, which means that this line should be a first degree line. So from this point to this point, we will draw a linear line, first degree line. And this ordinate 35.25 is equal to the reaction present here. So this will bring it to 0. So now we have the shear force diagram for this beam. This part AB is positive, and this part is negative. Here we are. We have shear force diagram and bending moment diagram. Sorry, we have shear force diagram, and next step is to draw the bending moment diagram. For bending moment diagram, let's draw the 0, 0 line, reference line. 0 and 0. This is BMD, and the units will be kilonewton meter. Now at point A, if you look at the values of moments for portion AB, how much is the value of bending moment at point A, at support A? It is equal to positive 80 kilonewton meter, and at point B it is 108.75 kilonewton meter. So this is 80, let's say this is 80 kilonewton meter, and at point B it is 108.75. All right. Now the question is, how should we join these 2 points? First degree line, second, third degree line. For that, we will have to look at the degree of governing equation. Here is the equation of bending moment for portion AB. 5.75x minus 80. What is the degree of this equation? Degree of this equation is 1, because the highest power of x appearing in this equation is 1. It means that these 2 points should be joined with a linear line. Here we are. So we have joined this 80 and 108.75 kilonewton meter with a 0 degree line. Next, at point B, how many different values of moment do we have? We have only one value from portion AB. We got MB equal to 108.75 kilonewton meter, and from portion BC, again MB is 108.75 kilonewton meter. So we have this one value for point B. What is the value of bending moment at point C? At point C, it is equal to 0. It means that the bending moment diagram will be connected here at the 0 point. Now, next question is that how should we join these 2 points? Should we join them with a first degree line, or second degree, or third degree one? For that, we will have to look at the degree of bending moment equation, and in this case the degree of equation is 2. The highest power of x in this equation is 2, so the degree of this equation is 2. It means that these 2 points, this 108.75 and this 0, should be joined together with a second degree line. So second degree line, the next question is that whether it should be convex up or concave up. For that we will have to look at the magnitude of shear force diagram. If the magnitude of shear force diagram is increasing, then the slope of bending moment diagram should also be increasing. And if the magnitude of shear force diagram is decreasing, then the slope of bending moment diagram should also be decreasing. So from point B to point C, whether the magnitude is increasing or decreasing, I'm talking about the absolute value, the magnitude. The magnitude of shear force is increasing. It means that the slope of bending moment diagram should also be increasing. And how we can draw such line? This is a second degree line whose slope is increasing from this point to this point. If you draw a line and like tangent at this point, and you look at the slope of that tangent, and you record that, and then you draw a tangent at this point, and you determine its slope, you will see that the slope is increasing from this point to this point. So this completes the bending moment diagram, and for this beam, the entire bending moment diagram is positive. The entire bending moment diagram of the beam is positive. Bending moment diagram is closing at this point. Value of bending moment is 0. This is a check. Bending moment diagram, if it closes, then it means that this diagram is correct. Last step is to draw the elastic curve, and as the entire bending moment diagram is positive, then the elastic curve will be sagging throughout the length of the member. So here we are. This is the elastic curve of the beam. It is sagging throughout the length of the member. So this completes our discussion about this problem. We have drawn shear force diagram, bending moment diagram, and elastic curve. So we will stop recording here. Thank you.